So when an earthquake happens, it releases the energy in the form of seismic waves. Now, as we know, there's two types of energy. There's potential energy, which is energy that's just stored up. And then there's kinetic energy, or the energy of movement as it's actually moving. When an earthquake happens, it releases that potential energy into kinetic energy, and we see that in the form of waves. And these travel away from the hypocenter or the epicenter in all directions. And these are used to locate and measure the magnitude of an earthquake. By measuring these waves, that's how the scientists can tell how strong the earthquake is. Now, there's two types of waves, and we call those primary waves and secondary waves. And the reason we call them that is because of when they happen and also how they happen. Primary waves are what we call longitudinal. Let me show you what I mean. Here's a piece of paper, okay? Now, I'm going to take this paper and I'm going to fold it in half, and then I'm going to fold the sides out like an accordion fold, okay? Like an accordion fold. Remember, we've done accordion folds before. We sure have, okay? So I'm just going to keep folding this, okay? So as the Earth's surface, and remember there, as the Earth's surface moves around from each other, let's say that there are two plates that come together as compression, okay? Then they're going to push together, and when they do, watch what happens to that energy. It just springs right back out. They push together, and that energy springs right back out. But it goes in a straight line. They're compressed waves. As P waves or primary waves travel through matter, that matter is compressed and expands. So it pushes together and pushes apart. The waves travel through the Earth just like a sound wave travels through the air. Oh, check this out. Okay, I've got the slinky, and watch this. See this? See all those up and down coils there? Watch what happens when I touch this one and then let it go. It makes movement all the way across. I'm going to do it again. Okay, I'm going to take this one and then let it go. And look at how it keeps moving back and forth. They travel through the Earth just like these waves travel. A compressional wave looks just like that, okay? So secondary waves are also called shear waves, and they involve more of a side-to-side motion rather than a straight-on motion. Shear waves, you can also look at a slinky, and look, if I do it this way, then that force, that energy goes down the slinky and then comes back. But when it comes back, it hits more energy that's moving down. And so you'll notice the first time it goes back and forth, and then it starts bouncing up and down like that. That's because those molecules are colliding and they can't keep going in a straight line, so they have to go somewhere and they go up and down. Pretty cool, huh? All right, I know what you're thinking. You're thinking, big deal. What does all of that mean to me? We have learned so much about tectonic plates, and we've learned about shifting, and we've learned about movements, and we learned about this stuff here. Why in the world do I care? I am so glad you asked. Here's the thing. We need to make sure that we build our structures earthquake-proof. Now, here in Oklahoma, we have recently seen a lot of earthquakes. Yeah, they happen where our structures were never built to withstand earthquakes, so this is all a brand new idea for us. So I've got a great way we can test earthquake structures. We can test structures against earthquakes. You're going to love this. This is what you need. You need some Jell-O. You need some marshmallows. You need some spaghetti. And that's all. Yeah. So what I did, I went ahead and made some Jell-O, and there it is. And then I took some spaghetti, and really, I mean, don't cook it. Get it when it's still in the package like this, and then get these little mini marshmallows like this. Get those little mini marshmallows. Okay, so you can see I've got some marshmallows here, and I've got some spaghetti that I broke down. And let me show you what I made. So I made them ahead. Okay, so it's all about shapes. It's going to be the same structure. So I've got a triangle there, and I've got a square here. So which shape do you think is stronger? Let's take a look. If I set this down right here, and I push, if I set this down right here, and if I set this down right here, see, I can't even set it down and it'll do something. But if I set this one and I push down, look at that. That's much stronger because the force here is pushing out and then is pushing around, and the pressure is making it bend. Okay, here with the triangle, it's actually pushing down on both of those legs equally, and it's making it support more. Now let's take it a step further. If I take a bunch of triangles and I make them into a pyramid, that's what I'm going to get, and that's going to be stronger. If I take a square and make it into a cube, then it's still going to have a problem, and you can see right here, it won't even hold itself. See, it moves around like that without shaking out. But if I combine the two shapes, the square and the triangle, look at this. So I combine the shapes. Now look at this. If I do that there, and I push down there, and I push there, because that force is pushing out away, and it's got a tension and compression. Compression means pushing together. Tension means pushing apart. That force is pushing it out, but the compression is holding it together, and that's working there. So then I took this one step further, and, well, I'll tell you that in a minute. Let's try this first. I'm going to put my pyramid here on my Jell-O, and look at that. It's shaking and moved around, and it did all that. Then I'm going to take my cube that I made, and I'm going to put it right here. And you can see even before it starts shaking, it's already falling over. But if I take that one step further, which I did, and I've got right here, I've got the cube, and you can see that all around I've got those triangles in there, and I even built a top on it. Look at this. See? This is almost like a design challenge, okay? So you can do anything you want to. Get your marshmallows and your spaghetti and put it on a bed of Jell-O like I did and shake it around, and you can see that that's moving around there, but this is standing so much stronger right there. How cool is that? So here's what we learned today. The Earth's crust is made of shifting plates which are slowly moving around on the Earth's surface. When two of these plates collide, it can cause that surface to vibrate. This is the shaking that's known as an earthquake, and we know that they can go next to each other, or they can push across and then want to go under, or they can pull apart, right? And these are called faults, that line that comes there. Certain structures are able to withstand more shaking than others. Shorter buildings lower to the ground are preferable to taller buildings because the low center of gravity acts like a fulcrum in a lever. The taller the building is, the further the ends are from the bottom, and they're going to sway more. And the force of a disturbance like that in an earthquake or in the wind is going to be multiplied, okay? Certain shapes like triangles and squares, we're able to use those in structures, and when we combine the two, it makes it even stronger, especially if you put them near the bottom part. That's because there's no way to bend a triangle without breaking one of its joints, okay? So, if you had fun today, say, I had fun. And if you learned something, say, I learned something. So glad you did. Can't wait to see you next time, right here in the Mad Science Lab.